US Physics Olympiad, year 2018. F equal MA. Exam B. In this year, this exam was splitted by 2 different days, and you can participate either in day A or day B. That was the same condition for participation. 25 problems for 75 minutes. Please subscribe for this channel to get more interesting problems. Problem number 1. A large lump of clay is dropped off of a wall and lands on the ground. Which graph best represents the acceleration of the center of mass of the clay as a function of time? Solution for problem number 1. During free fall, the acceleration is constant and approximately negative 10 meters per second square. It spikes up during the landing and remains zero afterward. If we check all possibilities here, we have only such behavior for acceleration in case B. Initially that's negative, after that it spikes positive, and after that it remains zero. Such behavior we can see only on case B. Other cases they are wrong. So that was a solution for problem number 1. Problem number 2. A uniform block of mass 10 kg is released at rest from the top of an incline with a length 10 meters and inclination 30 degrees, and slides to the bottom. The coefficients of static and kinetic friction are mu static equal mu kinematic equal 0.1. How much energy is dissipated due to friction? Solution for problem number 2. To solve this problem, we need to find what is work done by force of friction, and this work equal to force of friction multiplied by distance, which is 10 meters, and we have this expression: work equal force of friction, which is mu k multiplied by mg cosine theta and multiplied by distance L. After putting numbers, we have 87 joules. This is the answer D, and this is a correct solution for problem number 2. Problem number 3. A 3 kg mass moving at 40 meters per second to the right collides with and sticks to a 2 kg mass traveling at 20 meters per second to the right. After the collision, the kinetic energy of the system is closest to. Solution for problem number 3. Because this collision is absolutely inelastic, first we can find what is the speed of center of mass. That will be this expression. After that we can find what is total kinetic energy. That will be this expression, and after when we put numbers, we have 2560 joules, which is closest to answer C, 2600 joules. And this is the answer for question C, and this is correct solution for problem number 3. Problem number 4. A basketball is released from rest and bounces on the ground. Considering only the ball just before and just after the bounce, which of the following statements must be true? Solution for problem number 4. The momentum of the ball isn't conserved since it experienced an external force from the ground. The kinetic energy isn't conserved either, as the sum of it is dissipated into sound waves, vibration of the ground, vibration of the ball, etc. So it means that the correct answer is E. Neither the kinetic energy of the ball nor the momentum is conserved. That was solution for problem number 4. Problem number 5. The hard disk in a computer will spin up to speed with 10 rotations, but when turned off, will spin through 50 rotations before coming to a stop. Assuming the hard disk has a constant angular acceleration alpha 1 and the angular deceleration alpha 2, the ratio alpha 1 over alpha 2 is next one. Solution for problem number 5. From one hand we have during acceleration final angular speed omega square equal 2 alpha 1 theta 1. From other hand, this omega square equal 2 alpha 2 theta 2. It means that alpha 1 multiplied by theta 1 equal alpha 2 multiplied by theta 2, and from here we can find that alpha 1 over alpha 2 equal theta 2 over theta 1, which is 5. This is answer D, and this is solution for problem number 5. Problem number 6. A massless beam of length L is fixed on one end. A downward force F is applied to the free end of the beam, deflecting the beam downward by a distance x. The deflection x is linear in F and is inversely proportional to the cross-section moment I, which has units meters power 4. The deflection is also depending on Young's modulus E, which has units newtons per square meters. Then x depends on L according to next one. Solution for problem number 6. According to data, we have x proportional to force, y proportional to I, and also it depends from length L with the unknown power alpha, and depends from Young modulus with unknown power beta. We know that dimension for Young modulus is kilograms by meters power -1 and the seconds by power -2. Force dimension kilograms power 1, meters power 1 and seconds power -2. Cross-section moment I has dimension meters power 4 and length has dimension meters power 1. So it means that when we use this data, we can put them in first proportion and find that we have this equation for dimensions. From here we can compare dimension for meters, that will be this one, and for kilograms, from which we can find that beta equal -1. We can put this beta in this equation for meters and find that alpha equal 3. It means that x must be proportional to beam's length L power 3. That's answer D, and this is correct solution for problem number 6. Problem number 7. A pendulum of length L oscillates inside a box. A person picks up the box and gently shakes it vertically with the frequency omega and the fixed amplitude for a fixed time. To maximize the final amplitude of the pendulum, omega should satisfy next value. Solution for problem number 7. In the frame of the box, vertical shaking is equivalent to having G oscillate with the frequency omega. To increase the amplitude, gravity should be strong when the pendulum is moving down and weak when it is moving up. So because it happened twice, when the pendulum moving down and moving up, there must be 2 oscillations per oscillation of the pendulum. So we have omega must be equal 2 times square root from g over L, which is answer A. That was the solution for problem number 7. Problem number 8. The coefficients of static and kinetic friction between a ball and the horizontal plane are μs equal μk equal μ. The ball is given a horizontal speed but no rotational velocity about its center of mass. Which of the following graphs best shows the rotational velocity of the ball about its center of mass as a function of time? Solution for problem number 8. The kinetic friction force, μ multiplied by normal force, applies a constant torque, so the angular velocity initially increases linearly. After it begins rolling without slipping, the angular velocity remains constant. If we check all 5 possibilities here, only graph C showing this behavior for angular velocity. Initially it's linear and after it's constant. So that's the correct answer for problem number 8. Problem number 9. A 3 kg ball moving at 10 meters per second east collides elastically with a 2 kg ball moving 15 meters per second west. Which of the following statements could be true after the collision? Solution for problem number 9. We can see that total momentum in the initial frame of reference is 0. It means that it must be 0 after collision too. And also because we have a absolutely elastic collision, speed of each ball must be the same as before collision. Only direction could be different. If we assume this possibility, we can see that only in case E we have this possibility. In that case, the ball with a mass 3 kg must move directly to the north with a speed 10 meters per second. And this is correct answer E. And it was solution for problem number 9. Problem number 10. A balloon filled with air submerged in water at a depth h experienced a buoyant force B0. The balloon is moved to a depth of 2h, where it experienced a buoyant force B. Assuming the water is incompressible and the balloon and the air are compressible, the buoyant force B satisfied next conditions. Solution for problem number 10. The buoyant force is rho v, where rho is the density of water and v is the volume of water displaced. Since the water is incompressible, rho is constant, while v decreases since the balloon and air are compressed. So it means that b must be less than b0. And this is the answer D. And this is correct solution for problem number 10. Problem number 11. A circle of a rope is spinning in outer space with an angular velocity omega 0. Transverse waves on the rope have a speed v0 as measured in the rotating reference frame where the rope is at rest. If the angular velocity of the rope is doubled, the new speed of transverse waves as measured in the rotating reference frame where the rope is at rest will be next one. Solution for problem number 11. Consider a small segment of rope. The tension force on each end of the rope provides the centripetal force, which is proportional to omega square. The wave speed is square root from tension over linear density. Linear density here is a constant and t proportional to omega square. It means that the speed proportional to omega. And this is answer C, and this is a correct solution for problem number 11. Problem number 12. A child in a circular rotating space station tosses a ball in such a way so that once the station has rotated through 1/2 rotation, the child catches the ball. From the child's point of view, which plot shows the trajectory of the ball? The child is at the bottom of the space station in the diagrams below, but only the initial location of the ball is shown. Solution for problem number 12. The child catches the ball, so the path must start and end at the child, running out choice E and A. To decide between choice B, C, and D, consider the velocity the child observes at the moment the ball is thrown. At this moment, the ball is moving directly upward, while the child is moving directly to the right. So the relative velocity is directed both upward and leftward, giving choice C, and excluding B and D. Because for B we have only speed going to the center of this station, and in choice D we have only leftward motion. It is possible to solve this problem exactly, though this wasn't necessary. In polar coordinates, the radius r of the ball is linear in time, and the angle theta of the ball is also linear in time, because it is constant in the lap frame, but the child's frame rotates uniformly. Explicitly, we have r proportional to theta minus pi over 2 for theta belong from 0 to pi, and plotting this gives choice C. That was a solution for problem number 12. Problem number 13. Two blocks of masses M1 2 kg and M2 1 kg are stacked together on top of a frictionless table as shown. The coefficient of static friction between the blocks is μs equal 0.2. What is the minimum horizontal force that must be applied to the top block to make it slide across the bottom block? Solution for problem number 13. Let's write equations for motions for the top and the bottom blocks. For top block we have mass m1 multiplied by acceleration a equal force F minus force of friction. For bottom block we have m2a equal force of friction. It means that acceleration equal force of friction divided by m2. From here we can find what is force F. Force F equal force of friction multiplied by m1 plus m2 over m2. But the maximum possible force of friction equal mu static multiplied by m1g. So when we put this to this expression, we have force F equal this expression, and when we put numbers we have 12 newtons, which is answer D, and this is a solution for problem number 13. Problem number 14. A spool is made of a cylinder with a thin disc attached to either end of the cylinder as shown. The cylinder has radius r equal 0.75 centimeters, and the discs each have a radius big R equal 1 centimeter. The string is attached to the cylinder and wound around the cylinder a few times. At what angle above the horizontal can the string be pulled so that the spool will slip without rotating? Solution for problem number 14. For the spool to avoid rolling, there must be zero torque about the spool's contact point with the ground. This occurs when the string lies on a line that intersects the contact point, which we can show on the next picture. Drawing a right red triangle gives us this expression: sine 90 degrees minus theta equal small r over big R. From here we can find that theta equal 41.4 degrees. That's the answer B, and this was a solution for problem number 14. Problem number 15. You are standing on a weight scale that reads 700 newtons while holding a large physics textbook that is originally at rest. At time t equal 1 second, you begin moving the textbook upward so that by time t equal 2 seconds, the textbook is now half a meter high and once again at rest. Which of the following graphs best illustrates how the reading on the scale might vary with that time? Solution for problem number 15. Note that the center of mass of you and the textbook begins and ends with a zero velocity. Therefore, the average reading on the scale must be equal to the combined weight 700 newtons. There is an upward spike on the beginning because you exert a sudden upward force on the book to get it to starting moving, which thus exerts a downward force on you. Similarly, there is a downward spike at the end. The only possibility for this motion could be explained in graph E, where we have positive spike in the beginning and a negative spike at the end. That was a solution for problem number 15. Problem number 16. A plane can fly by tilting the trailing edge of the wings downward by a small angle theta, called the angle of attack. In still air, a plane with a ground speed v will have a lift force proportional to v squared theta, and the drag force is proportional to v squared. Consider a plane initially in level flight in still air with a constant ground speed v. If the plane enters a region with a tailwind with the speed w less than v, the wind is blowing in the same direction that the plane wants to fly. How must the engine power and the angle of attack change for the plane to maintain level flight at the same ground speed? Solution for problem number 16. Let u be the relative velocity between the plane and the air. To keep the lift force the same, if u decreases, then theta increases. Since the drag force is proportional to u squared, the power supplied by the engine is proportional to u cubed, which decreases. So it means that the correct answer is C. The engine power decreases and the angle of attack increases. That was a solution for problem number 16. Problem number 17. A pogo stick is modeled as a massless spring of a spring constant K attached to the bottom of a block of mass M. The pogo stick is dropped with the spring pointing downward and hits the ground with the speed v. At the moment of the collision, the free end of the spring sticks permanently to the ground. During the subsequent oscillations, the maximum speed of the block is next one. Solution for problem number 17. When this pogo stick reaches the ground, it's still accelerating down because force of gravity equal mg and the force from compressed spring is small. But when spring is compressing, it reaches the force of compression equal to mg, and in that moment when the net force equals 0, we have a maximum possible speed of this pogo stick. So it means that we can find what is this compression for this pogo stick spring. So we have mg equal kx, and from here we can find that x equal mg over k. Now we can use energy conservation. Suppose that the potential energy for gravity when this pogo stick just reached the ground is 0. It means that total energy of this system is just the kinetic energy for pogo stick, and that's equal 1/2 mv square, and that must be equal to kinetic energy of this pogo stick in the point of x compression, which is 1/2 mu square, plus potential energy for compressed spring, which is 1/2 kx square, and minus potential energy for force of gravity, which is mgx. Now we can insert this expression for x in this equation and find that 1/2 mv square equal 1/2 mu square minus 1/2 m square g square over k. And from here we can find what is this maximum speed. That will be u equal this expression. And that will be answer E for this problem, and this is the solution for problem number 17. Problem number 18. A spring of relaxed length L1 and a spring constant K1 is placed in parallel with the spring of relaxed length L2 and the spring constant K2. A force F is applied to each end. The combination of the springs acts like a single spring with the spring constant K and the relaxed length L, where we have next expressions for K and L. Solution for problem 18. To solve this problem, we just need to write equation for force. From one hand, this force equal combined force from both strings, which is this expression, and from other hand we have this force must be equal to regular force from combined springs with the constant K and the relaxed length L, which is this expression. Now from this equation we can find what is K and what is L. We just need to equalize coefficients for polynomial with the x and the other free member with the 0 power. From here we can find that the coefficient k just equal k1 plus k2, and the free member give us this expression. It means that now we can find what is relaxed length L. That will be this expression. It means that the answer is this one, which is answer B, and that was a solution for problem number 18. Problem number 19. In an experiment to determine the speed of sound, a student measured the distance that a sound wave traveled to be 75 plus minus 2.0 centimeters, and found the time it took the sound wave to travel this distance to be 2.15 plus minus 0.10 milliseconds. Assume the uncertainties are Gaussian. The computed speed of a sound should be recorded as following. Solution for problem number 19. In this solution we use fractional uncertainties. Since speed equal distance over time, we add the fractional uncertainties of the measured quantities in quadrature, given next expression. dv over v equal this expression, which is 0.054, and speed equal 75 centimeters over 2.15 milliseconds, which is 349 meters per second. And now we can count what is a dV. That will be 19 meters per second. And the final answer is 349 plus minus 19 meters per second, which is answer E. That was a solution for problem number 19. Problem number 20. A massive uniform flexible string of length L placed on a horizontal table of length L over 3 that has a coefficient of friction mu static equal 1 over 7. So equal length L over 3 of a string hang freely from both sides of the table. The string passes over the edges of the table on smooth, frictionless, curved surfaces. Now suppose that one of the hanging ends of the string is pulled a distance x downward, then released at rest. Neither end of the string ever touches the ground in this problem. The maximum value of x, so that the string does not slip off of the table, is next one. Solution for problem number 20. First, let's write equation for force of friction. Force of friction equal mu static multiplied by mass of part of this string, which is on the table, mass of whole string divided by 3. And if one end of this string is released by distance x from one end, we have equation that force of friction minus x over L mg equal x over L mg. And finally we have this expression to find what is x, and x equal L over 42, which is answer A. And that was the solution for problem number 20. Problem number 21. A uniform bar of length L and mass m is supported by a fixed pivot, a distance x from its center. The bar is released from rest from a horizontal position. The period of the resulting oscillations is minimal when x equal which one? Solution for problem number 21. This bar is a physical pendulum, and for physical pendulum we have a formula for period. Period equal 2 pi multiplied by square root from I over mgx, where I is a moment of inertia, m is mass, g is acceleration of free fall, and x is distance from the pivot to the center of mass. For uniform bar we have a formula for moment of inertia I. Due to parallel axis theorem, that's equal 1 over 12 ml square plus mx square. Now we can put this expression to this period formula, and we have period equal this expression. To find what is condition for minimal period, we have to find what is the condition for minimum of this function under the square root. For that we have to do first derivative from this function. This is the function. For the extremum of this function we have first derivative equal 0. It means that we have this equation, and after all x equal L over square root from 12. Also we can find what is this period. Minimum period equal this expression, but the answer for this problem is x equal L over square root from 12, which is answer B. That was solution for problem number 21. Problem number 22. Two particles of mass m are connected by pulleys as shown. The mass on the left is given a small horizontal velocity and oscillates back and forth. The mass on the right will behave like this. Solution for problem number 22. The mass on the right will oscillate because the tension in the string oscillates. However, it cannot oscillate horizontally because there is no torque exerted on it. Suppose it oscillates horizontally with no net motion. Then the average y component of the tension acting on the mass on the left is equal to mg, but the x component of the tension is non-zero. Then the average magnitude of the tension is greater than mg, a contradiction. Thus, the right mass must instead oscillate and move upward. This is the answer B. Oscillates vertically and with a net upward motion. That was solution for problem number 22. Problem number 23. Two particles with mass m1 and m2 are connected by a massless rigid rod of length L and placed on a horizontal frictionless table. At time t equals 0, the first mass receives an impulse perpendicular to the rod, giving it speed v. At this moment, the second mass is at rest. The next time the second mass is at rest is next one. Solution for problem number 23. The motion is the superposition of two motions, uniform translation of both masses with the speed. V center of mass equal this expression, and the circular motion about the common center of mass, where the first mass has a speed v1 equal this expression. The second mass comes to rest again after one period of circular motion. The radius of motion for the first mass is equal to this expression. So after that we can find what is a period. That will be period equal to pi r over v1, which is, after we use these two expressions, 2 pi l over v. That's answer A. And this is the correct solution for problem number 23. Problem number 24. A particle of mass m is placed at the center of a hemispherical shell of radius r and mass density sigma, where sigma has dimensions of kilograms per square meter. The gravitational force of the shell on the particle is next one. Solution for problem number 24. By Newton's third law, it is equivalent to find the force of the particle on the shell. The pressure exerted on the shell is this one. P equal gm sigma over r square. Now consider a closed hemisphere filled with a gas of pressure P. Since the hemisphere cannot move on its own, the net force on the flat face is equal to the net force on the curved face, which is equal to area of this flat face multiplied by pressure, which is pi gm sigma. And this is answer E, and this is the solution for problem number 24. Problem number 25. A student is measuring the surface area of a cylindrical wire. The student measures the radius of the wire to be 1 plus minus 0.1 centimeters, using a ruler, and the length of the wire to be 1.00 plus minus 0.01 meters, using a meter stick. The precision of their results can be increased in several ways. First one, upgrade the ruler to a caliper with uncertainty 0.01 centimeters. Second one, upgrade the meter stick to a tape measure with uncertainty 0.001 meters. Third one, Repeat the measurement independently 10 times and average the results. How do the resulting uncertainties of the measurements compare? Solution for problem number 25. In this solution we use fractional uncertainties. Fractional uncertainty of an average of n independent trials is decreased by a factor 1 over square root from n. The surface area is proportional to radius times the length, so we add the fractional uncertainties in the quadrature. Then for the first method we have this formula, which is 1.4%. For the second method we have about 10% uncertainty. For the third method we have uncertainty 3.3%. Then method 2 has the highest uncertainty and method 1 has the lowest. The answer for this problem is D. And that was a solution for problem number 25.